Hello, everyone, and welcome. It's a real pleasure to be presenting here at the 34th International Materials Research Congress. Today, we're diving into some exciting research titled Enhanced Acetone Gas Sensing Performance of GD-Doped ThesNO2 Thin Film Synthesized by Ultrasonic Spray Pyrolysis for Non-Invasive Diabetes Detection. Essentially, we're going to explore how tweaking materials right down at the nanoscale is opening up some incredible new doors for early, non-invasive medical diagnostics. Let's get right into it.
Here's a quick look at our agenda for today. We'll walk through the introduction, methodology, structural and morphological results, gas sensing results, sensor dynamics, and finally wrap up with our conclusions.
Starting off with Section 1, Introduction to Non-Invasive Diabetes Detection.
So as we all know, diabetes mellitus is a massive global health challenge. And one of the biggest hurdles? The disease is often completely asymptomatic in its early stages. Right now, what the clinical world desperately needs are detection methods that are accurate, cheap, and, most importantly, non-invasive. No more finger pricks, right? This is where acetone in exhaled breath comes in as a fantastic biomarker. When glucose metabolism changes, breath acetone goes up. So our main objective here was simple but ambitious, to develop and evaluate thin-film gas sensors using tin dioxide, both pure and doped with gadolinium, to effectively capture those tiny, minute traces of acetone on the breath.
Moving to Section 2, let's talk about our methodology for sensor fabrication and testing.
To build these films, we went with an ultrasonic spray pyrolysis system, or USP. Now, if you've worked with USP, you know it's a real game changer for straightforward, cost-effective, and highly controllable thin film fabrication. We deposited our pure and gadolinium-doped tin dioxide films over 3 distinct time windows: 90, 110, and 130 minutes. Once that deposition was done, we calcined the samples at 450 degrees Celsius for 2 hours just to really lock in and consolidate that structure.
After synthesizing the materials, we obviously had to put them through their bases. We used XRD, FTIR, and SEM to really dig into the structural properties of the films. Then came the true functional test, the gas sensing chamber. We used a microheater to precisely hold the operating temperature at 300 degrees Celsius. Under those thermal conditions, we constantly monitored the electrical resistance of the films while hitting them with controlled bursts of acetone, ranging from 1 all the way up to 500 parts per million.
That brings us to Section 3, Structural and Morphological Results.
All right, so what did the XRD and infrared analysis actually tell us? Well, they confirmed a single phase of tin dioxide with a tetragonal rutile-type structure. No secondary phases popped up at all, which is great because it proves the gadolinium was perfectly incorporated into the matrix. We also saw a very clear preferential orientation along the 200 plane across all films. But here's the really cool part. The gadolinium doping caused a massive drop in crystallite size. We went from roughly 46 nanometers in the pure samples down to about 22.5 nanometers in the doped ones. Shrinking the crystals like this is huge because it drives up structural defects and lattice strain, which, as you know, is exactly what you want if you're trying to trap gas molecules.
Looking at the topography under the scanning electron microscope really drives this point home. If you compare the 90-minute pure film with its gadolinium-doped counterpart, you can see both maintain nice, uniform surface coverage. But the gadolinium clearly acts like the brakes. It inhibits individual crystalline growth. It totally modifies the particle size and leads to this distinct surface agglomeration. And that's exactly what we're looking for. This finely tuned, bumpy morphology essentially means we have a significantly higher number of active sites ready to interact with the surrounding gas.
Let's move on to Section 4, Gas Sensing Results, the moment of truth.
So when we finally exposed these samples to acetone, they all showed a sharp drop in electrical resistance. Total classic N-type semiconductor behavior when exposed to a reducing gas. But the performance gap between the samples was just night and day. The pure tin dioxide films, they only gave us a response of around 5 to 40%. But the gadolinium-doped films, they absolutely smashed it, exceeding a 70% response rate. Our standout performer, without a doubt, was the gadolinium-doped film deposited for 90 minutes. It peaked at a really impressive maximum response of approximately 73% when exposed to 500 parts per million.
Next up is Section 5, Sensor Dynamics.
To understand what's happening dynamically, we have to look at the mechanism. The acetone molecules are basically reacting with oxygen ions that are already hanging out, adsorbed on the film surface. That reaction dumps electrons right back into the crystal lattice, and bam, that's your drop in resistance. In terms of speed, the response times were incredibly fast, consistently under 30 seconds across the board. The recovery times took a bit longer, hovering between 400 and 700 seconds. But that optimal 90-minute dubbed film we just talked about, it clocked a response time of just 28 seconds and recovered in 504 seconds at 500 parts per million, all while showing fantastic cycle-to-cycle repeatability.
Y finalmente, Section 6, Conclusions.
To wrap this all up, our research conclusively demonstrates that doping tin dioxide with gadolinium successfully restricts crystal growth and creates highly beneficial structural defects, and those physical changes translate directly into vastly superior acetone gas sensing capabilities compared to using just the pure material. Out of all our tests, the gadolinium-doped film deposited for 90 minutes hit the perfect sweet spot, delivering the best overall performance, rock-solid repeatability, and incredible sensitivity. It's safe to say this material is a seriously viable candidate for the next generation of portable devices designed for non-invasive diabetes monitoring. Thank you for your attention.